So good morning to all, especially to the panelists and to all our guests and viewers. So this morning I'm going to talk about our project, research project, and that is called Design, Development, and Prototyping of Robotic Sprayer for Uniform Surface Thickness Applications. Robotic sprayer or automated sprayer, no? And of course, I'm Engineer Charlton S.E. now, the presenter for this project, representing the Lyceum of the Philippines University in Batangas. So our title, to reiterate, our title is Design and Development and Prototyping of Robotic Sprayer for Uniform Surface Thickness Applications. And actually, we are two authors here because we have done this in Ethiopia a few years ago. I'm Engineer Charlton S.E. now, and then my partner in Ethiopia is Engineer Ahmed Endris, the supervisor in Bishoftu Automotive Industry, Defense University College of Engineering is the university that is affiliated in Bishoftu, Ethiopia. No? So let me read first the abstract. This project is conceived to address the requirements of uniform painting thickness problem in the bus body painting process of Bishoftu Automotive Industry Corporation. At present, all the painting activities are done manually, which results to inconsistent quality of paint surface thickness to bus panels. The manual painting also takes much longer time, meaning less productive, and poses health hazards to the operators, like the paint and fumes. Not to mention the physical fatigue incurred by the laborers when doing the painting processes the whole day. The robotic sprayer was developed using mechanical engineering and mechatronic disciplines with automation and simulation softwares that are commercially available. The machine incorporates a geared motor for rotating the lead screw that transports the spray gun holder mounted on the nut and carriage platform. The pneumatic cylinder actuates the spray gun trigger, and the number of sensors are located at a specified part of the machine for defining the limits of travel or the motion of the system, and to transfer the other parts of the bus to facilitate other painting operations. Same controller responsible for controlling the flow rate of paint coming from the spray gun by controlling the exact distance of the lever, which is actuated automatically by a small piston operated by a two-way single solenoid directional control valve. All these discrete devices are controlled by a programmable logic controller, the Siemens Logo 12/24RC, or relay contact, relay control. The relay ladder logic diagram and functional block diagram was meticulously designed and was used in programming the PLC using Siemens Logo software, TIA, or Total Integrated Automation. The machine further includes a frame where the painting component carriage is mounted and driven by a geared motor. In this project, critical factors such as mechanical and structural loads were considered to design calculations. The system components, parts, and the assemblies were modeled analytically before the actual production. The modeling and production drawings were accompanied or accomplished through CATIA version 5, release 19, and ANSYS Mechanical APDL software package. The new spray paint were compared to that of manual painting system to see the effectiveness and quality of paint by analyzing the uh, uh, speed of spray gun motion and by measuring coating thickness painted on the surface of the bus. From the comparative analysis between the manual and automated painting process, 36.84 of uniformity of paint improvements from the existing system was achieved, and 62% of labor or manpower participation was completely reduced. Therefore, the newly designed machine is highly recommended to replace the existing manual painting system. And we have these keywords: coating thickness, degrees of freedom, PLC or programmable logic controller, Siemens logo 12/24RC, three two-way single solenoid valve, and lead screw carriage. Okay, so background of the study and statement of the problem. So the background is this. Now, the study was conducted in Ethiopia, where I serve as a professor in a military university, one of the biggest and most complete university in laboratory in East Africa. So uh, we had this partner corporation, Bishof, the automotive industry, and it is located in Bishof, Ethiopia, somewhere in 2017, 2018, that year, no, where there is a surge of rejects of painted bus panel in that mentioned year or period. So just a brief background of Bishop, the automotive engineering industry. It is an Ethiopian manufacturing and assembly center for heavy armaments, tanks, and military vehicles. It is one of the organizations of the Ethiopian defense industry supporting the Ethiopian National Defense Force. Because when I was in Ethiopia, the university I was serving is under the Ethiopian National Defense Force or under the military. No? So that's why the military school and the industry or corporations are in partner, and they are working hand in hand. No? So Bishop to Automotive Engineering Incorporated is situated is in a very large area in that city, and there are five departments, and they are as follows. No? Tanks and armored vehicles manufacturing, rebuild of all tanks and armored vehicles used by Ethiopian forces. The military vehicles manufacturing, where there is a mechanical workshop, there are manufacturing departments for engines, and they are producing spare parts for tanks and armored vehicles also. Medium and heavy weapons manufacturing and electroplating section. So they have that department. Communications apparatus manufacturing and maintenance section. Repair and maintain various communications apparatus and electronic equipment in use with the Ethiopian forces. So here, as you can see, there's a motor manufacturing and mechanical workshop. So they are also manufacturing civilian buses and cars. Now, aside from military services and military transport engines and trucks and cars that are used by Ethiopian defense forces. So this is Ethiopia, the map of Ethiopia, to give you a brief background. So here is the capital, Addis Ababa, and somewhere 45 kilometer down, not west, is Bishoftu. So this is where the Bishoftu Automotive Engineering is located, and also the university that I'm working for. So here are the buses for the that are being manufactured in that corporation. So here are the buses, single, and this one, no, it's like a double bus horizontally. Excuse me. So here are the buses, and here is the plant. So one time there is this the famous president from Rwanda, President Paul Kagame, visits Bishop the automotive uh, industry. No? He is there, and statement of the problem. So, what are the problems that are needed to be addressed by this project? There is an inconsistent quality of paint distribution to bus panels. No, so some are thicker, some are thinner, some are rough, and some are smooth. So there's also the manual painting also takes much longer time, meaning the productivity is less, and it poses hazard to the operator. No? So the longer you are exposed to fumes from the painting, um, spray or paint spray, no, it's dangerous to the health. Not to mention the physical fatigue when doing the painting for a longer period of time within the day. This process basically possesses redundancy of painting process, uses of operators inefficiently, inconsistent thickness of paint, and possesses ergonomic and safety issues to the operator. This project would like to address the issue of quality, efficiency, and safety by designing automated spray painting system. So our objectives, we have two, the general one and the other is specific objectives. The general objective is to design and develop and fabricate or prototype an automated painting or robotic painting system or a machine for bus body panels to achieve an efficient and good quality painting operation in Bishop the automotive engineering industry. So the specific objectives are number one, to design and fabricate the lead screw mechanisms platform for X and Y motion or the horizontal vertical motion of automated painting system to attain an acceptable or equal distribution of paint throughout the body or bus panel. Number three, to design and develop PLC program or codes suited for the automated painting system and to perform a real-time validation of automated spraying system efficiency as against the manual operation. So those are our objectives. So scope and limitation, the project covers only a translational or straight rectilinear motion of a spray gun and in 2 degrees of freedom, meaning X and Y only. The Z-axis was not included in the study. Also, the movement uh, is in Cartesian plane of 2 axes only. No cylindrical or spherical motion included in this study. And we have this delimitation, the project's limitations in terms of resources, which explains why a scaled down prototype model, like it was 1:10, was rather produced the rather than the actual dimension. So we go now to the methodology. So our methodology is divided into five sections, and that is one, data collection. Number two, concept design and selection. Number three is mechanical design. Number four is automation and controls. And number five, manufacturing of prototype. Yeah. So that is how we approach our approach for the study as a whole. No? And then, of course, there's a validation and testing at the end. So here is the bus that we use in the study. We visited the corporation and we were able to coordinate with the officials there. No? So lucky enough, during that time there was this painting of the bus. Now I think at this point of time it is still in the primer. Now they are coating primer on the bus, and this is the same bus that we were able to use during the study. So it is supplied, the body is supplied by Yutong, I think from China, and it has a dimension of 11.4545 meter in length, 2.5 meter in width, and 3.56 meter in height. Now there are 8 employees participating in the painting section for finishing one bus with 8 hours interval. So within the 8 hours, there are 8 employees that um, are working together, no, for this one bus. So the amount of paint for the completion of one bus needed is a total of 14 liters. Now 14 liters the volume, 8 liter normal paint. The composition is 8 liter paint. Then there's a hardener that is amounting to 4 liters and 2 liters thinner. And distance of nozzle tip of spray gun to bus is zero point 0.2 meters or 1, 2, 3. How much that's it's like 200 millimeter, right? So 20 centimeter. So here is 20 centimeter or 200 200 millimeters. So let me get 200 millimeter, right? Yeah. For obtaining a good quality of paint. Now, from such type of paint mixture, the following coating thickness was taken by considering 8 points on painted bus body, shown below as a sample when one round of paint is performed using an instrument called micron. Okay, so there was this 8 points. Now, for example, there's a panel. Yeah, so there's a panel of our bus body panel. So there was this 8 points, no, and you have to get measurement from these 8 points to get the thickness, and below are the example of the results of the thickness being gathered. Now, uh, the spray gun that we use for the automated is the same as that of the manual, and here you can see it's like an inverted it's in a flip or inverted way. What we did here is we measured the so-called canopy, meaning the um, the measurement, no, the distance from the bus body up to here, no, as mentioned, is 20 centimeter, and also when you put the spray, no, when you put the spray gun, so it will have only a this one, right? It will have only so it will have only 20, no? So here is also 20 centimeter, right? So 20 centimeter in length, or 200 millimeter, no? So we use this data, no, for the incorporation in our automated spray. So it says here from 15 to 20 centimeter, depending on the pressure, no, from the compressor, of course. So it's 15 to 20 centimeter. So we could say that it is like if you're going to put that in a tolerance form, so it's like 17, no, nominal 17.5 plus or minus 2.5, right? So that is the the coverage of the spray, right? So we go now to the concept development. Now, how do we design the automatic spray painting system? There is a concept development phase that we follow, because we are following, and we have this subject of product development and design, and I was also the professor in product design and development. So we started the concept, no, up to the course of development. So there should be a problem or a statement, no, or something that needs to be improved. Then we have to identify the customer's needs. Now, in this case, that is the Bishop the Automotive Engineering Corporation. They need to have consistent thickness of coating in the established target specification. We have to establish the target, the thickness. Now, there's a specification in terms of thickness. Generate product concepts, meaning the concept alternatives or design. We will discuss that later on. Sales product concepts, I think it's optional. It's not more select product concepts. We have to select the product concept or the design concept, no, 3 to 5. So we introduce, we generate 3 products, as I'm going to explain later on. Then the product test, we test the product concept, or at least evaluate. Then we can set the final specifications, and then plan the downstream development. Now, as you go to the manufacturing, right? So this is just for concept development, right? So now, um, how did we establish the target specification? So our target specification is established based on the machine that is going to be designed, and manufacture or to undergo prototyping with with the following criteria. So we lay down the criteria as to 1 up to 10 based on the needs, and then we are going to evaluate it like a grading, no, like a grading exercise from some standards, no, like 5 is the most important. Right now, 5 is excellent, 4 is good, 3 is medium, and 2 for low, no, or 1, right? So if I may invite your attention here, no. So here is our grading. It should be consistent. 5, 4, 3, 2, and 1. So going back here, um, obtain the uniform point of distribution. Of course, that's very important, very critical, and very it's paramount to the study. Increased rate of painting, so not so much with the uniform distribution, so we graded that as 4. Allow large area of coverage of painted spray. It's also important, but not that much, so we make it 4. Paint spray gun distance to the bus body, it's 5 now. The distance is very important and can be maintained with readily available materials. Now, it's also very highly important. Ease of manufacturing, no, is 4. Noise and the compactness of size, more on ergonomics and aesthetics or physical attributes. No, so it's 4. Efficiency, it should be efficient 4. Minimize labor participation, 3, because whether we have other people, the important thing is the distribution, no, and the uniform distribution. So we made it 3, and low material cost is 4. By the way, the importance was graded by a committee, no, by a group from us, from researchers, and from the designers, and also from the customers, the bishop of the automotive engineering. No, so concept selection for drive mechanism. Actually, this whole exercise is called the Pew. There was this person from Ireland, no? Pew concept selection method. So Pew concept selection method. That is the standard method for product design and development. Pew concept, now selection method. Pew. It is called. It is pronounced as Pew. Pew. Now, we have to select the drive mechanism, and we were able to generate 3 concepts. No? And these 3 concepts are for drive mechanism. They are as follows. Number 1 is A, which is this one, lead screw. The other is rack and pinion, meaning gear, and the other is like a fluid actuator, which is hydraulic. So to give you visual or an image of what we're talking about here, this one is the mechanism for lead screw. No? So where is the lead screw here? So as you can see, no, here is this, right? And this one, the dark area. So it's a lead screw. It's always used in machine tool building and the machine shop. No, there's a screw and the nut. No, there's a partner between the screw shaft and the nut. No, so the nut is traveling. The nut is traveling, and this one is the one that is fixed. No, it's just rotating. So the linear motion or translation is being affected by rotary because there's a DC motor, DC motor somewhere here, and another DC motor somewhere there. So when the motor rotates and it is coupled, mounted, no, in we mounted with a lead screw, it will produce a rotating, but at the same time, it can produce a linear, no, or translation due to knot, because the knot is the one traveling, no, so the one that is traveling. So let me put another color, no. So this is the concept number one, and in this portion, it's just the stand, no? Because we need to have a stand, no? And we are not yet complete. We are planning in the future to have a wheel, no, and automate the wheel. But for now, for the sake of academic requirement and academic presentation in research, we just put the C channel here, no, as the foot, no, or the peg for the project. So here is a round shaft as a guide. No, this is the guide, and there's the bearing block. Roller guideway. This is a roller guideway. No, circular rod, and they are made of steel frame. No? So this is the carriage. Now you are going to put the carriage in. So what is important here is the vertical, right? The vertical carriage and also the horizontal carriage to be affected by this lead screw, and the vertical by this lead screw. So it's just up and down and then right to left. Okay. Now the second concept was with the use of gear and rock, now rock and pinion. Now, so this is the pinion, now in mechanical engineering term, and this is the straight rack, now like a guide for the spar gear for the pinion, right? So this is the so-called rack, yeah, okay. And this is the carriage where you're gonna put the mechanism like the paint and so on, no? So this is another, right? And also, I think our last is hydraulic cylinder drive mechanism for spray painting. No? So we also thought of fluid power actuators. So basically, it's a cylinder like that. No? So there's a cylinder and there's a piston, and this is the rod. Okay. So in order for you to visualize, if I'm gonna make it in 3D, no, so it's like a cylinder, meaning there's an area, circular area, and the length, no, so that's a cylinder, the geometric basic figure. But inside there's a plate or a disc, it's called piston, and what is mounted in the center, the center of the piston is the rod, piston rod, and this is the piston plate, right? Piston plate. Okay. No? So what it's going to do is if there's a fluid, no, inlet, when the fluid enters, whether air, if it's pneumatic, but in this case it is hydraulic oil because it's hydraulic, meaning it's liquid, then this piston plunger or plate will go up now because the fluid will come here, right? So let me correct the drawing. So if the piston comes here, it will be filled with fluid, pressurized fluid. So if there's a pressurized fluid and you have an area that is circular, right? So you have an area, you will develop a force, right? From the elementary definition, pressure is force over area. That's why the force will push it upward. Or when you utilize this, another port, it will push the piston rod downward. No? So that's why it is double acting cylinder. No? So this port A This the port B. Okay, so we will, of course, we will put the spray gun here, no, at the tip of the plunger or the rod. Now, this is the rod, right? This is the rod. Yeah. So we'll put the spray so that once the cylinder is going upward, so it can spray, right? So which among the three are we going to use? There is some systematic method for evaluating and deliberating this. Now, so that is called Pew selection method, if I may write it again now. So Pew, Stuart Pew from Ireland. So what you're gonna do is you select the criteria here: ease of manufacturing, speed, ease of maintenance, noise, lubrication, cost, and efficiency. These are the criteria that we used also a while ago, right? It is, I mean, somehow related. Now, efficiency, noise, and others. So those are these are the selected criteria from among the chosen criteria. So we just sorted out, no, the most important criteria, and we're going to put weight, no, because it's this pew selection method is the selection by importance, no. So you're gonna assign how much weight is manufacturing, no, 25%. How much weight or importance the speed is 15%. Ease of maintenance is 10. Noise is 10. We don't want to have a noisy spray, of course, because the compressor is already noisy. Then the lubrication use, the cost is also important. It is 15, and then this is 20. So when you total this, when you add all this, it should have 100%. Now, the rating from our initial exercise. Now, for example, if I may get this, ease of manufacturing. Uh, yeah, here, right? Ease of manufacturing and others. So you will have a rating also from the group, no, from the design design people, the design committee, and all the stakeholders like the users, no, and the officers, the decision makers, and so on. So we put here rating is 5, 4, 5, 4, 5, 4. Okay, then all you have to do is to get the weighted score, and that is going to be point 2, then it's this point 27, this point 5. You just have to multiply the two values, point 5, then point 4, and then this one, point 33, and point 2. So that's weighted. And then you go to the next, which is the rack and pinion. So you have to give I score 2, no, because it's more difficult, no, and then speed is 2. No, this one is 4, meaning higher. This is higher, can yield a higher speed, no, of travel, rather compared to the gear. And then here, if you're gonna compare, they are equal, right? And this is 5 lubrication. You need to have good lubrication. This one is 3, and then cost 5, a bit higher. This one is 4, and this one is 4 and 4. This one, the lead screw is of the advantage. So because here is 2 only and 2 only. So all you have to do is to again now get the weighted score for this. Now, so all you have to do is to get the weighted score. You get the total, and then you divide each item. So like here, no. So you get the score. You can get this when you get the total, and then you divide by the from the individual now. So also here the rating is 3, not 3, and then 5. Why is it 5? Speed, because cylinder, you can have good speed if you have a very good valve or the tank, right? And then the ease of maintenance, it's hard to maintain the hydraulic. It's hard because the tank and the pressurized fluid will yield some leakage in the long run, and the heat of the fluid. So the oil tank will be heated, and you can only manage that if you will put another device that is a cooler, oil cooler, and that's another investment. No, so those are the things. Lubrication, three, and then cost, three, and then efficiency is five, right? No, so and then all you have to do is to add all the weighted score. No, so weighted, you just add, then you will get 2.3, then 2.03, then this one is 2.9. No, so by the numerical score, you can rank according to Pew selection method, which is the drive mechanism that you intend to continue, because of this evaluation. So here is the lowest, 2.03, the rack and pinion. Here is the second, and this is the first, right? So here, yes, are we going to continue to develop this? So we said yes. This one is no. This one is no. No, because this one has the highest rank now based on the weighted percentage, right? So we decided to continue with the concept one, which is using the lead screw. That's why we were able to come up with the lead screw. No? To further validate, the or to substantiate the evaluation, you can continue the pew selection method with evaluating or deliberating the merits. When I say merits, you can put plus now for its positive or meritable attributes. Now, for example, here, lead screw is of manufacturing. Of course, you're just going to machine it, right? Three, rack and pinion, meaning it's less, because you're going to manufacture the rack, you're going to manufacture the pinion. So that adds more complexity. Hydraulic, it's just difficult unless you order it now. But if you're going to build it, build to per order, no, you have to build it based on a specification. That's gonna be more difficult because you're going to manufacture the cylinder and the piston, and then the seat, and then all the O-rings and the like a gasket, no, yung O-rings to prevent leakage, no. So speed, lead screw is highest and it's more precise because of the pitch. No, rack and pinion is only two, and then hydraulic cylinder is only two. No, it depends on the pressure being given. Ease of maintenance, so two, they are all equal, I guess. Noise, two. Rack and pinion is high. Hydraulic is low because it's only fluid. It has less noise, right? So but the pump could have a noisy. So that means it was rendered low, right? This is the legend. I almost forgot. So here, so low merit, right? So cost, right? So when you talk of cost, it is affordable. I mean high. No, this one is medium, and this is also high. Hydraulic cylinder. Efficiency, lead screw is efficient and it's precise. Then this one is not so much. And then here is also uh, more on precise. Lubrication use, lead screw, only this, no? This one, rack and pinion, it needs high, because the frequent contact of pinion, the pinion gear and the rack, and hydraulic cylinder, it has always the lubrication component because it's using oil, and you need the lubrication in other parts. Compact size, I think they are all equal. Okay. So these are the another way of selecting the or testing the concept, no? So what we decided here is the concept number one, no? Based on few selection method because of the merits, now that we were able to evaluate. And then here is the theoretical or technical model framework. What we have here is this dynamic model of the whole system. It's more on the dynamic or movement, no? Types of cylinder, you need to know the type of screw, fatigue of guideway, length of flexibility or the precision of length of screw. Then here, the type of cylinder or actuator, nozzle, diameter, spray performance model of spray painting, speed paint, precision of coating. That's the result. Meaning this is in the spray gun, no, in the trigger. This one is in the guideway, right? Then this one, performance of model or carriage, type of material, then the speed motor, the geometry is are the inputs, and the portability, weight of carriage. So these are the metrics. No? This is the model, the inputs, and these are the model for the outputs, the metrics. Because how do we evaluate? We can evaluate through metrics. No, is it portable? Is it lightweight? No, weight of the carriage, right? This one is speed of the paint, I mean paint gun, then precision of coating, right? Here is the length of flexibility and precision length of screw. So you just have to know and design the type of screw and the type of the shaft or the cylinder. Okay. So here design of mechanical elements and automation design for spray painting mechanism because we already decided for the lead screw mechanism. So here is the design. We have to have a bearing pillow block here, no? So the seat where the seat of the shaft, no? So it has a bearing, but the shaft will go in the center or the middle, and then this is the lead screw, no? The specifications were able to design and get the pitch and the other, no? The number of entry, or is it right hand or left hand? Then we just put the spray gun here, no? So this here is a spray gun. It is mounted here. That's why it can go, no, upward and downward because it is mounted on the nut. Okay, nut. NUT. Okay. So that is the whole mechanism, isometric view of the carriage with accessories. No? So the carriage is this as a whole. So it is carrying different components, the spray gun, and then the pillow block of with the bearing, and also the lead screw. Okay. So what we did here is we identified the materials, and then the projected amount of material we were able to identify, and then we calculate the weight, no? So how did we calculate the weight? We cut the material. So we cut the material. We have a shop there in the university. So for example, sheet metal. So we cut this. Also length, width, and then there's a thickness. Okay. So very easy, very practical way is to use weighing scale. So we scale, we put them into weighing scale, then we're able to measure each weight, no? So 9 kilogram, including the PLC and the electronics. This one is 8 kilogram, and so on and so forth, right? So all in all, the total mass of this carriage mechanism and its accessories is roughly 41 kilogram. And why do we need to know the weight? We need to know the weight of this mechanism because we have to manufacture a structure that will or that can withstand the load, that will carry this, that can carry this. Now we have to have a structure, a metal structure that can carry this, right? For example, the platform or the table, no, because this is the load, no. So from that load, we should be able to know the dimensions of the platform, because the platform will be the one who will accommodate all this mechanism. No? So that's the principle. Why do we get? Why? How did we get the different weights? No, or the total load weight. Okay. Now, the following will be the mechanical part, which is the design. And I don't have to elaborate this though, because it's not a full lecture. It is just a presentation. So what we did are the series of design for the major components. For example, the lead screw. This is our criteria. It should be strong, it should be highly machinable, and so on and so on. We could do the following. We could test the strength. We could bend. We could draw the bending diagram and the shear diagram and so on and so forth, just to design a lead screw. So it's a lot. It's a really hard work, full hard work. Now I just get the excerpt from the full paper. Now the paper is submitted in the to the panel now and to the organizing committee now. But I just put some to show that we really had very serious work done with respect to mechanical design now, because we are both mechanical engineers. We help each other now in the calculation. So this is the shear and moment diagram. Now, so vertical shear, and this is the moment diagram to know which part of the system will incur a very high load, no, and what kind of load, no. So normally it's it's just a weight load, no. So this the concentration of weight, and then this the shear diagram and the moment diagram. So also, as I told you, I'm not going to discuss the calculations because it's a lot. It is comprising half of the project work, the project documentation. So what I'm gonna do is just to reiterate, no, and maybe I'll just focus on the automation or the robotic part. How did I do the program? How did I do the automation? Because this is standard, no? It's mechanical. So the design of nut, how do we select the motor, the torque, no? At what kind of rating, and what kind of service, no? So it's all there. No, I just I just capture, I just screenshot the part, so that to show you that there's a lot of serious and tedious mechanical design work being put into this project study. We also designed the keyway. No? So there's a shaft for those who are not mechanical engineer. No? So there's a shaft, no, a solid shaft. Then once you are going to couple some another part, no, so you have to machine this, right? And this is the key, and this portion is keyway. So if you redraw the shaft, sorry for my drawing, but here is the shaft now, no? Yeah, cutaway view. So meaning this is the cut portion of this, no? So you're gonna insert that, no? The key you're gonna insert in the keyway. So we designed the keyway, you know, because there's a design there for, you know, dimension, no? There's the breadth, width, and the height, yeah. And then you will have to experience some forces or stress like shearing, no, and bearing, yeah. So shearing and bearing will affect the keyway. So here is the formula. I'm not going to discuss this due to time constraints, no. So here, once we design the key, so you will have the width and the height and then the length, no. So these are the important in the key design. width, height, and the length, and then depending on the shaft diameter, I think we have the 33, 35 uh, millimeter diameter, no, in that lead screw. So it's you have to just choose if your diameter, shaft diameter, is falling within this range, then you just have to get this following dimensions of the key. Now 8 by 8, then you just have to get this. Now within 32 to 133, it's a long range not to choose from. Yeah. So we also designed the bearing. No. So these are the symbol for the bearing, and then normally the load is always at the middle, and you can design the bearing with the following formula. And also there's a formula for the bearing. Yeah, so we use the SKF. It's a commercial, so every bearing has also their own standards and formulas, so we follow the formulas for the SKF design, so that we could arrive with a correct diameter, and also the bearing life. No. Yeah. So here is the continuation of the bearing, now thrust bearing. Then we were able to select the frame of for the supporting system, because we are going to get the to carry the carriage or hold the carriage. So we just need a table, no, for the meantime, to utilize, so that all these things here can be accommodated. So we need to have a kind of platform, no? And then we just have to calculate the slenderness ratio, no, with all this formula, right? We are going to use column formula. So the column load, or the column bending, no, load. So I just got it from the document. So I just extract it, so that you can see how much mechanical activities have we put into this project. So welding, because a lot of these structures we are going to weld. So we're going to weld that, we're going to weld this and the other. So we have a particular section for welding, and also the painting system and component. Now this is the common painting system. To replace the use of hand, we just use the cylinder, right? The pneumatic cylinder, so that when we trigger the cylinder, it will go retracted. No? So it will go there, retract. When it retract, then it will have this nozzle tip open, and then it will spurt. Now it will throw the mixed paint, now intended for the bus panel. Now that is what we're done. So we were able to design the pneumatic cylinder. So the design of the pneumatic cylinder is very easy. Just need to know the this diameter. So how to you calculate the diameter? So it's there, right? So it has to do with the pressure, force over area. No, so you could know the the dimension, because you have the pressure and the force developed, you know, because you have the area. Now you will know the area now, because pressure times area is the force. If you know the force that needs to actuate this trigger, right? So the trigger of this gun, now you need how much force. Now we already calculated. So we need the force here, and then we have the pressure. We can get the area, right? So pressure, force over area. The pressure is coming from the compressor, and the force is, we already calculated how much force is needed to actuate this, no, this gun. And then you can get the area, and area is simply when you cross multiplies force over pressure, right? And of course, to expound or decompose this, pi d squared over 4, this is constant both. Then you can get the square diameter. You can get the root of that. You extract the root, and you will have this diameter for the cylinder, which is 19.99. And of course, you know that in a practical, it is not available. Who will give you 19.99? Nobody. So the next higher is 20 millimeter. Now, so based on design, we have to use 20 millimeter diameter. So those are the mechanical works that we have done, the serious mechanical design in order to put up a machine like this. Now, so here is this. Here is the motor, no DC motor that will drive this lead screw. Here is the motor, another motor that will drive this, no, up and down. And this is the spray gun. And there's a cylinder here that will trigger the handle, right? So these are just the guide for the carriage so that it can move like X, no, and positive and X negative, and here now on this side, yeah, vertical, no, positive and negative, right? Yeah. So this is the project or the prototype that we did, no. But the video and other pictures are left in Ethiopia. I wasn't able to get. No? So we'll just access it when I contacted our research partner, Engineer Ahmed Andres. So now we will go to the automation part. We finished with the mechanical because we've also, before that, we finished with the concept development. How did we choose the concept? Then we finished the mechanical design. Now I want to focus on the automation part. No, so we will discuss this thoroughly. So now we are in the automation system, the automation part. No, what makes it automated? So this is the wiring diagram for the automated bus body spray painting system to both motors and solenoid. No? So I'll try my best to explain this so that the audience could understand. Um, so let me have this here, right? So normally the control of any system is composed of the two parts of a circuit. No, so one is control control circuit, and the other is power circuit. Circuit is where the relays and the sensors and the other switches are mounted, and the other circuit is power, which I think I put here at the bottom because of the constraints in space. No? So I think here, yeah, here's the power circuit. No? So the power circuit consists of the power devices, which is this one. In this case, we only have the two motors, right? Um, the two motors. Let me put here, right, so that everybody will understand. The motor one for vertical, right? No, movement or motion. No, so motor one, right? And then the other is motor two, which is for the horizontal. No, so basically what I'm saying is the the carriage will go up, and that is because of the motor, right? Because of the motor that is attached here. Yeah, so it will turn the lead screw, and the lead screw has the nut, and the nut is where the carriage is mounted. Now, so here's the motor, here is the nut. So the once the lead screw is rotating, now it's perennially rotating. So this is the nut, and in that nut, the carriage is sitting upon, right? So this can travel up and down because the DC motor that we have is counterclockwise, meaning by now bidirectional. meaning it can move clockwise and counterclockwise. So that's the part of motor one here, right? So as you can see here, now if I make it right, so this is motor one, now up. Where is our, yeah, here? So here is motor one up, here is down, right? Here is down, and this one is right, going to the right. No, so this circuit basically simulates the the cycle, not the cycle, one cycle that we use. Now we did not intend to paint the whole bus and showing all the circuits now, because it's gonna be lengthy. It could be very tedious. So we pick up like a one cycle. The motor will go up as it sprays. No, it is spraying while it is moving up. Now, for example, this is the spray gun. Yeah, here is the triggering is the cylinder, right? So once the cylinder uh, goes retracted, yeah, once it retracts, it will trigger the triggering handle. Then it will give uh, spray, no. But this one should go up, no, I mean this carriage should go up. It's going up so that it can um, spray here on the vertical, right? So that's the essence of the motor one, and the motor one up, right? And this one motor one down. When it goes down, this one is going to the rightward, right? So now let me give justification to this circuit, so that all of us could learn, no? So look at this, no? So we could say that this is the bus bar, that is line one and line two. And when we're talking of control system, we are dealing with the low voltage. So what we use there, because it's controlled by PLC, 24 volts DC. And this is just representation of the relay ladder logic that we implemented. Actually, we don't have the actual relay, because the relay is inside the PLC. It's here, right? So these are the internal relays that I use in programming the Siemens. No, but just to show you the principle, no, from the actual relay, I can show you the sequence. So we need a start. Now the standard is we need a start and stop, and it's being represented by these two devices. So here, start and stop. So all we have to do is to press this start in this momentary push button, or the so-called mushroom. So if that is the case, the power will come here now. So as you can see, I'm putting some kind of lines now, because we already contact made a contact in start, and the stop is normally closed, so the power can go here, right? And then the relay 6 contact is normally closed, so the electricity or the power can go here, energizing R1. No, so when the R1 is energized, no, the coil is energized, all the contacts will be affected. So we're gonna look for all the R1, R sub 1, no? So it will be closed, right? It will be closed, so this one will be closed, no. But since this one is not yet, no, it is not triggering the S1, so nothing is happening now. So look at this, at the power. What is R1 responsible for? Let's look at this. As you can see, there are two motion that the R1 could be responsible for. Now, when it gets close and this one gets close, motor up, meaning if we put clockwise, now because it is powered by relay, no? It is powered by relay or contactor. I use a relay. I think there are eight contacts now. So when it's powered by relay or contactor, so once the contact is being closed here, so let me use another. The electricity from line one to line two, no, will be active. So from the line one, look at this, yeah. So the electricity will travel like this, and this is already closed because of the R1 contact, yeah. So the electricity will flow, and this is also closed, no? So it can just pass through. So energizing the DC motor, no? So this is the DC motor. It will energize. So what will happen is this, no? The motor will go up because it is powered. But at the same time, if you will see here, no, so another electricity flow will come because R1 is there. So it is normally closed, normally closed, normally closed. So it can go here, and this is also R2. This is also normally closed. It can pass through and then energizing the solenoid. Why solenoid? Here, because this one is powered by solenoid, no? Because you know solenoid is just an electromagnet that can affect a motion, no? There's a force, so that force will tend to make the solenoid switch over, no? So the valve, I mean, so this is the solenoid, and this is the spring, so it will switch over. So from here, no, so from here, three two-way. Now this is three two-way valve going to the atmosphere, and then this one is going up. So it will switch over before it is here, then it will come here. So it will give a pressure here. No, if gives a pressure here, because we reverse the mounting of the hose or the polyurethane, so it will go retract. No, so from forward it will retract. Then it will pull pull the trigger. When you pull the trigger, then it will spurt some uh, pink, no? While the motor is here, no? The motor is here. So the carriage, the whole carriage, now it is driving the the so-called lead screw, and then this is going up. So while it's going up, no, here, no, while it's going up here, then it is painting the bus body now, because this is the bus body, right? So this the carriage where it handles it carries the spray gun, right? So that's why in the control circuit there's this description of motor one up, meaning the motor one is responsible for the vertical here. The motor one is responsible for the vertical, and then the solenoid valve is on. So when it's on, it will pull. It will pull the trigger, and it will spray, you know. So that's it. And then we put some sensors like electromechanical switch or the inductive and capacitive sensors. So and they are represented by S1. Look at this. Now, once look at this. Once the carriage reach the limit in vertical, now it will go up like a 40. Now we designed it like 40 centimeter, and the horizontal is 20 centimeter. When it goes up, there's a sensor here, right? There's a sensor here. It will just define the limit, no? We have sensor here and we have sensor at the bottom. So we define the vertical distance where the lead screw could only travel. So once it reached the limit in the upward direction, so let me put here. Look at this. This will close, no? Right? So this switch or sensor will close. And once this is closed, so the electricity can travel here, right? It will travel here. I'm just putting a kind of shading so that you will see. But R1 is closed already, no, because of this, right? R1. So it will go to R2, right? So all the R2 will be affected. So this will have a latch, no, or logic or latch. It is called latch, even though the sensor is being open, it's still already latched. So the power or the current can also come here at the parallel. No, how did you see it's parallel? This one, right? This one is parallel to this. This one is parallel to this. No, parallel. So that parallel is or logic in PLC, right? So look at this. We just finished this. So R2 is responsible for what? I think there are three: motor, 2 is up, meaning is activated. Now motor is this motor 2? Now motor 2 is up, so it will go that way. Then solenoid valve off, because you already have painted up to the top. So you just have to stop the solenoid valve to stop the paint gun, no? So you have to off the gun and then M2 to the right, no? So here M2 to the right. So the motor should travel to the right, no? So the motor should travel to the right. Okay? So it goes to the right. Okay. Now, how did we see that? Now, there are three. Motor 1 up, solenoid valve off, and then M2 right on. So you go to the power circuit. How is that happening here? So here, no, if you're gonna see this, no, this one, motor 2 right, no? Look at this, motor 2 right, di ba? So this one is motor 2 right. How did it happen? Because of energizing the relay 2. So you look at all the relay 2, this one, no, R2 is closed, and then here, R2. So look at the R2, look at this, R2, yeah, R2. So the electricity will come here. Let me shade it like this. Yeah, R2. This one is already closed. So it will energize the motor, the responsible going right, no? So here in the horizontal motion, yeah, here. So if this vertical, the motor is here. Here is the going to the right, no? Because this one is right, left, up, down. No, so here is the concerned motor that we are talking about right now, because it's going to the right side. No, it's going to the right side. No, so that can be reflected here in this circuit. No, so R2 will energize the motor because this is already normally closed. Then it will energize the motor. What else? Can you see another R2 somewhere? No, so R2, what about this? No, so here R2 solenoid normally close, it will open, no, because once the R2 is activated, it will open. Okay, so if I put that in the original, yeah, look at this. No, so R2, look at this. What I want to emphasize is this, right? The motor 1, when R2 is activated, look at this. When R2 is activated, no, the electricity will flow here. It will go here, and then go here to activate M2, no, the motor to the right. Once it's moving to the right, what's happening to other R2? This will stop. No, so this is normally uh, close, R2. It will open, right? From normally closed, it becomes normally open. So it will, yeah, if that is the R2, it will open. Yeah. So if this the R2, it will become an R2 of normally open. Yeah. So motor 1 will stop. And also this will be cut, it will become open. Solenoid valve will stop. Why should it stop? Because you're finishing the vertical, right? So once you reach the limit, it will the limit switch. It will give signal to R2. No, as you can see here. Look at this. No, so the sensor there will give signal to R2. So the R2 now, if you can see, once it's energized, the coil, the contacts will be affected. So it becomes open. So this open motor 1 that is going upward will stop, and R2, the solenoid, right? It's normally closed. It will become open, so it will also stop from painting. Now, because it is pulling the trigger. Now it is going forward again. Now that is how we design it. Another is this R2. Once it is off, this one will become on, right? The current can travel now here. What does it do? It will pass here in R3, then it will energize the motor that is responsible for going to the right, no, rightward. No. Okay? So if I may summarize, this will stop, upward will stop, the paint will stop, and then this one will go to the right. So if I may illustrate this, so coming from here, now this one is our dimension, that is 40 centimeter, and this one is 20 centimeter. So once it reach here, there's a sensor, right? Sensor here in the person of S1. So we put the sensor as S1. So what will happen right now is this is S1. So the S1 will give signal to R2, and then the R2 coil will affect the contact. So this will become open. The motor will stop here, no, so because it's open. And then this is open. The solenoid will stop to paint. Now from here, it's painting, it's painting, it's painting. Then it will reach the topmost because of this now, and then the solenoid will stop because this will become open, the R2. And what is the other duty of the R2? You should be able to find out because you have the diagram. So R2 is also responsible. Now it will pass R3, motor 2 rightward, meaning here. So your motor 2, this motor 1, right? Motor 1, right? Going up. Motor 2 is going to the right. Okay, so this is rightward, meaning the X. This is motor 1, the Y. Okay, so it will only travel 20 centimeter of a distance, no? And the vertical is 40 centimeter. Now, once it reaches this, it will travel 20 centimeters so that it can position very well. Now, what is the logic here? The logic here is you can paint downward. No, when you open the paint, or you can open the paint gun, no, downward. So it will spray from top to bottom, and then also the vertical, which is M1, going down, right? So at this one here, M2, sorry, no. So this one is going down, no. So you can have the go down. So this one is going down. It will paint, no? It will paint from the top, top, middle, then bottom as it goes down. So that's why it will be activated by what? By R3. No? So how did you know R3? You go back there. There's something that triggers the R3, and that is S2. And where is the S2 located? No, it's located here at the 20 centimeter vertical. Now, so once it's here, now there's a sensor here. Once it trigger, then the going down will be affected now because there's a sensor here. What sensor is this? Sensor 2. So go back to the control circuit, find the sensor 2 here. Look at this, the sensor 2, it will go, the current will go here, then it will continue. This already normally closed because of this, no, to activate R3. So the R3 will be energized, and that is R3 is responsible for M2 right, meaning M2, the motor going to right, and M1 going down. I told you it is on the top. First, it will go to the right because it wants a 20 centimeter, no, canopy distance, because that's the width of the spray gun. No, the canopy or the area that it can encompass is 20 centimeters. So the motor will go here in the X. Then now you can go down. Now, so the motor one again will go down. So that's the responsibility of R3. No, R3. Look at this, R3. So all the R3 will be affected. This will become latch. This will become preset. and then look at this on the power. So find the R3 now. So the R3 now is this, no? It will trigger the motor down because it wants to paint downward because you already achieved the 20 centimeter uh, going rightward, not to give a distance so that it can spurt its canopy, no, its coverage of paint. So it will go 20 centimeter, and then there's this sensor. That sensor is S3 and S3 S2, I'm sorry, S2. So that is S2. It will give signal to R3. So R3, look for R3 all over the place. So R3 here, then the signal will come here, energizing R3. So once R3 is energized, the current can come here. This already close R4, that's NC. So it will go down. The motor now can go down here. Look at this. The motor now can go down, right? So it is this 20. First it goes up, stop, then it goes rightward. The sensor will detect, and then it can go now downward. And that downward, the responsible motor is vertical, right? Yeah, here. Motor one, down, because a while ago it is up. Now it's down. So it will go down while the motor is on, no? Because the R4 is, or R3 is on, right? The R3 is on. So that's the case. Now, if you want to continue, now I'm just saying that it's just a sequence. Now, once it goes down, it will touch S3. Now, this one is S3. Once it is going down, it will touch the sensor 3. So once it touch, it will trigger. It will become normally closed. The current can pass because this is already closed due to this. No, then it will trigger R4. So what is R4? You can also see all the contacts in R4. Make it close for the preset, then try to find the R4 in the power circuit. So where is R4? R4 here is the R4, right? So this one, R3 is closed a while ago, no? And then R4, it will open, so it can go to the solenoid, right? It can go to the solenoid. Why should the solenoid be active again? Because you're going to paint again, right? Going down, there should be some painting process happening so that you can utilize the downward motion or force. That's why here there's an R3. No, it's triggering the solenoid again. Okay, and that is the sequence. So we were only left one, I guess. So let me tackle this. So once you have S3, it will give signal to this preset, and then it will energize R4. So once the R4 is energized, that R4 is responsible for here. No, it will open the going down. No, because it's going down, it will stop. It will open, right? Because it's normally closed, it will become normally open. Then the motor will stop, and we do not know where. No, so it should stop such that it should go to its destination. So any R4 that you can see, this one, I think, is this R4? It's kind of covered, right? Now, so this is R4. Look at this, no? So this is a parallel. I would like you to look at this. So this is parallel, and this, no? So once it is closed, what happens this, right? The current can pass through. It can pass through also here, which is closed. Then it could bypass this, right? So here is the motor 2 rightward. Again, now motor 2 right. Now because it should go to the right side again, right? So here, so there's a sensor 4. You know, when you deal with the right, I mean the relay 4, then the sensor 4 will be closed. This will be closed, R4, R4. So if it is closed, then the power can now travel here and here, now energizing R5. So what's the responsibility of R5? Look at this. Is there R5 here? R4, R3. No, so that R5 is part of the circuit, right? So R5, R5, then R5, it will preset. Then when it reaches the another sensor, it will close, and then it will go to R6, which is reset. Reset means this one. Now this will become open. Now it's closed, it becomes open. So when it is open, so there's no power here, there's no latch, there's no preset, then there's no power here. Then no power here, no power here, and then this one is uh, going to be deactivated now, so all will be reset now in that particular case. So my point is it takes time to know. Now I take many years to study this circuit now, so uh, you can only understand if you grasp and absorb all this lecture on the relay control logic. It's a logic of ladder uh, form of bus in the circuit. No? So we already take up this, no, the power circuit and the control circuit. We will go now to the PLC because I use PLC Siemens. No, I just show you this no manually so that I can show you what's happening or you can review. So this one is the actual Siemens logo. You can save that as PDF. That's why I was able to send the PDF or screenshot. No, so all this same thing. No, so normally open is just contact. No, normally open. This one is normally close, right? So normally close. So this one is output instead of circle or others. No, so it becomes close and open parenthesis, right, for the output. So here is for the actual power devices. Now it's like open and close, like this one. Yeah. So we have four outputs now. So what I'm trying to convey is this. So the relay ladder logic in manual is converted to PLC because this one is inside the device. No, so I just use the logic for elementary electrical tracing and programming. Then you can program. You can use the sophisticated program using the simulation for the PLC Siemens. So this is the circuit for control, and this is the circuit for power. How do you know it's power? Because there's a power device. There's a motor. What else? There's a solenoid valve, right? So there's a motor and solenoid valve. So motor one, this one, no? So motor one is up, then later on, this one is motor down, will go down, right? So this one is another motor. Yeah? So just have to follow this. Yeah. So this one is another solenoid and output. No, so this one is solenoid for triggering the paint, and this one is the output. This one now, and it could be monitor also. So here are the list of materials like a BOM, no, bill of materials. We have a table, and then there's the specifications, and these are the devices, and then these are the materials, no, and so on and so on, so forth. No, so here is the cost. No, we run down all the materials and then the expected cost for this. Okay, so now the next is significant findings or results of the study, and then we'll go now to the summary and the conclusion and the recommendation, and that's uh, is trying to finish the this discussion. No? So at this point, we are going to discuss the uh, PLC ladder diagram, which is the controller circuit that is being used in the programming of the automated or the robotic spray. So this one is just the replica of what had happened when we are using the so-called um relay ladder relay ladder logic.